Right, let's go over this. So this is a process called Stork enamine synthesis. We're talking about this in the context of the alkylation, alpha alkylation of carbonyl compounds. So in the last class, we went over one type of alpha alkylation, or one way to alkylate carbonyl compounds to create alkylated ketones, right? Add R groups alpha to the carbon. We'll go over this again in a second, but I just want you to know that's how we're talking about this reaction, right? Alkylating. As you can see, in this transformation, what we're doing is we're adding this allyl group and making a carbon-carbon bond, right? So we're alkylating the carbon alpha to the aldehyde carbonyl. So the first step, first set of reagents is going to involve formation of an enamine functional group, right? So we're adding a secondary amine to an aldehyde. You can do a secondary amine to a ketone as well and make an enamine, right? And so I'm just going to give a really abbreviated mechanism for this enamine formation. And so we're going to get the enamine to form by addition of the secondary amine to the aldehyde. Right, and then we're going to go through a series of protonations. So we have an acid catalyst, we can protonate the oxygen. We have an extra proton on nitrogen, we can also protonate the oxygen. Right, and that's going to take us to an intermediate setup for eliminating water. Water is going to be kicked out, nitrogen electrons falling down and forming a iminium intermediate. Right? And then we form the enamine by pulling the proton on the carbon alpha to the iminium carbon. And pushing those pi electrons up to nitrogen. So when we focus on this enamine, we have our nitrogen with a lone pair, so a heteroatom with a lone pair, and that's next to an alkene or next to a double bond. What does that look like? What functionality does that look like? Something we've been using recently.
Enolate.
Good, it looks a lot like an enolate, right? So if we compare this to an enolate of that aldehyde, electrons up to oxygen. Right, hopefully you can see that we have the same arrangement of atoms, right? We have a nucleophilic atom attached to an alkene with a double bond, right? And just like whenever we take an enolate, use the oxygen electrons to push down, kick out the double bond to make this carbon nucleophilic, we can do the same thing with the enamine, right? Enamines have that same reactivity. So if you think about when we formed enamines last semester, right, we also looked at the hydrolysis, going from an enamine back to the ketone or aldehyde and secondary amine. The first step is going to be protonation of the carbon, right? So we're adding acid and water. The acid is going to protonate the carbon by having the nitrogen electrons fall down, kick out the double bond and grab that proton, right? In this case, before we put in that water, we're going to add a good electrophile, right? So when that electrophile is added in, that enamine is going to be able to act like a nucleophile. Right, so electrons and nitrogen will fall down, reform that carbon-nitrogen pi bond, and then we're going to kick out the carbon-carbon pi electrons to do an SN2 reaction on the alkyl bromide. Right, so we're making a bond from this carbon here in the chain, right, to the carbon that bromine is attached to. Oh, sorry, I forgot carbon there. Right, so the carbon-carbon bond was formed. Okay, see that we're back at the iminium intermediate. All right, so what's going to happen with this iminium intermediate? Can we go back to the enamine? Can we reform an enamine from this point? No, right? We don't have any alpha protons to pull to get back to that enamine, right? So we're kind of stuck at this iminium intermediate until we add the acid and water. And when we add acid and water, what's going to happen?
I think the water molecule will have to act as a nucleophile and kick out this cyclic amine.
Right, so water is going to act as a nucleophile, add to the iminium intermediate, right? That's going to get us back to this point, and we're basically just going back to the beginning, right? Back to the aldehyde. So this is going to be the hydrolysis of an imine. And again, I'm not going to draw all of the steps. This is a mechanism we went over last semester. Right, so we add water, do a couple proton transfers, get the proton onto the nitrogen, electrons and oxygen fall down, reform the pi bond, kick out the secondary amine, right, and we get back to the aldehyde. Any questions about that? Okay, so I will say for aldehydes, this works really well. For the alkylation of aldehydes, this works really, really, really well. And we'll go over why that is in just a second. Right, but it adds to the number of methods we know that we can use to make alkylated ketones, alkylate aldehydes. Right, so the first again is acetoacetic or malonic ester synthesis. Here we're doing acetoacetic ester synthesis, so we're starting with a beta ketoester. Treating it with base, pulling the acidic protons in the middle, adding our first alkyl group, in this case just R1. Right? If we want add another alkyl group, we can do that. Again, just treat with base, the appropriate base. Add the second electrophile. Right? And then the third step is going to be hydrolysis of the ester to the carboxylic acid, followed by decarboxylation. Right? So first we're going to lose methanol, and then we're going to decarboxylate to lose that carbon dioxide. Right, so the net effect of malonic ester, acetoacetic ester synthesis is the alpha alkylation of a ketone, right? We can add two alkyl groups to a ketone group. All right, for the Stork enamine synthesis, it's a little different, right? Up here, we're adding two R groups, and we can control where those R groups are being added because that central carbon in between the two carbonyls is the most acidic point, right? So we can selectively pull protons from that carbon and add electrophiles to that carbon, right? Here, we're typically doing a single alkylation event, right? So we're forming the enamine, adding whatever electrophile we want. The enamine acts as kind of like a enolate surrogate, right? And nucleophilically adds to that electrophile, and then we hydrolyze the enamine or the aminium intermediate that forms at the end. Questions about this? So we hope to add, the reaction we just did involved the addition of secondary amines to aldehydes. Right? When we add secondary amines to aldehydes to make enamines, there's only one option for the enamine that we can form. Right? Up here, we're adding a secondary amine to acetone, so this is a symmetrical ketone. Right? So it doesn't matter which side the enamine forms on, it's going to be the same enamine. right? Here we have an unsymmetrical ketone, right? So on one side of the ketone, we have two alkyl groups, right? On the other side of the ketone, we have one alkyl group, right? So think about if we're gonna form an enamine on this ketone, or from this ketone, what is the major enamine that will form? Which regioisomer of that enamine will be the major product? Right, think about the hybridization of the atoms involved in that enamine. Think about the geometry or structure that they have to adopt. Right? Consider steric interactions.
For the first line, can you draw the last step mechanism?
For here?
Yes.
Okay. Right, while I'm doing that, think about this one. Okay. All right. So if you were wondering about the mechanism for this last step, right, this is two steps. So we have a hydrolysis of the ester to the carboxylic acid. Just taking that carboxylic acid, rotate it around the bond identified with the blue arrow, right? Redrew it so that the hydroxy group is sticking up and the carbonyl is sticking down to the right. And then that's going to give us the best structure to show the decarboxylation mechanism, right? So we lose carbon dioxide, that forms the enol, and then that enol is going to tautomerize back to the ketone. Right? For this enamine question, right, we have an unsymmetrical ketone, so when the enamine forms, the double bond can form down the left-hand side towards the methyl group, right, or the double bond can form down the right-hand side, right, and we get a mixture of enantiomers. We're seeing a mixture of enantiomeric enamines. Right? Which one is most likely? Joey?
The one with it towards the methyl, because the amine is going to activate thermodynamic base in the organic product.
Okay, so you're identifying that this is going to be the more stable double
Yeah.
bond, right? The lower energy double bond, and that's true. So, if we're just kind of looking at the bonding pattern, right, this is definitely going to be the most stable double bond relative to this one. But the amine's not acting as a base, right? It's just acting as a nucleophile. Oh, I see.
At the end.
I see. Any other ideas?
It's gonna lie towards a more substituted carbon because if that double bond becomes functional, then there's a tertiary carbocation.
So we probably won't be doing anything with cations here, right? So whenever this is used as a nucleophile, nitrogen electrons will fall down, kicks out that double bond in that direction.
Yeah.
So that's kind of a nucleophilic or a negative center more than anything else. So no cations here. Yeah.
It's going to be easier to pull the hydrogen from this side.
Okay, so kinetically we can say it's going to be easier for the nitrogen to grab a proton from over here, right? So that might form faster. One thing I want you to think about is hybridization, all right? So and the geometry around these different atoms, right? So we're going to look at a couple of different atoms here. All right, so what's the hybridization of this carbon here? Oh man. SP, you just have to say one number after I say SP. So SP2, SP2, good. Right, so trigonoplanar, SP2. What about this one here? SP2, SP2. All right, what about the nitrogen? SP. Remember the nitrogen's in conjugation with the pi system, right? Good, so it's gotta be SP2 as well. Right, so that means that this nitrogen, this carbon, and that carbon are all trigonoplanar, right? So they're all in one plane, and then anything attached to those are also going to be in one plane. And what that means is that this atom here, this nitrogen, this carbon, and this carbon, they all exist in one plane, right? So you have this kind of this 5-member chain, 1, 2, 3, 4, 5, existing in one plane, and then coming off of this carbon here, you have 2 hydrogens. Right? And then coming off of this carbon here, you have 3 hydrogens. Anybody see a problem with that? Yeah, so Joey, what do you see?
A lot of steric interaction.
Yeah, a lot of steric interaction, right? So you're forcing all 5, whenever you form the double bond on this side, you're forcing all 5 of those atoms to be in one plane, right? And because they're in one plane, this methylene group here is going to have a lot of steric interaction with the methyl group down here. Right, so we'll draw that just kind of as opposing parentheses. All right, so because of that steric interaction, even though we would look at this and say that's the more substituted alkene, so this should be the lower energy enamine, right? In fact, it's the other one that's the lowest energy, right? Because this is going to be really difficult to form, really hard to get those 5 carbons all in one plane, right? So this will be the major enamine, and this will be the minor. Right? And so what that means is whenever you have unsymmetrical ketones and you do the Stork enamine synthesis, that synthesis or that alkylation that occurs is going to be regioselective. All right, so here I'm just drawing out a simple unsymmetrical ketone, right? So 3-methyl 2-butanone, right? Proposing this just the simple pyrrolidine secondary amine. Here's our electrophile, benzyl bromide, right? And then we're hydrolyzing at the end. And the major product that we should see should reflect the alkylation occurring on the less substituted carbon.
So in other words, it's the entire Markov.
Yeah, you don't want to really use that term. You can say it would.
It's just regioselective on the less substituted carbon.
Yeah, so it would react in a way. It would react in a way that would give us the kinetic enolate, for example, right? So we could also make this the same product, right? And this speaks to the third and probably most straightforward way of alkylating. Take that same ketone. Right, treat with LDA, THF minus 78, that's going to give us the kinetic enolate. Once we have the kinetic enolate, then we can throw in the appropriate electrophile. Right, and then if we wanted to just do a quick acidic workup, we can, but yeah, for this we don't really need to show that. We get to the product directly. Right, so the third way of alkylating is alkylation of lithium enolates. Right, and we've learned a couple of different ways to achieve the lithium enolates, to make the lithium enolates, right? One is LDA, and that gives us the kinetic enolate in unsymmetrical ketones. But we also learned about silylenol ethers, right? So using silylenol ethers to give us the thermodynamic enolate fully, right, without using a thermodynamic base. So silylenol ethers, treating them with methyl lithium gives us the appropriate corresponding lithium enolate. All right, questions about this? Okay, so this pretty much takes us to the end of chapter 17. We might go over one or two other reactions on Friday, just looking at some more contemporary Enolate chemistry. But for the most part, this takes us to the end. We'll start in on chapter 7, chapter 18 at some point on Friday.